So this is our final video on transition metals and transition metal complexes. And this video is going to cover what's happening to the orbitals in transition metal complexes. We're going to look at the colors of transition metal complexes, and we'll also touch on how transition metals and transition metal complexes can be used as catalysts. So we know transition metals all have electrons within their d orbitals. Now, when a transition metal is not bound to anything, we describe the 5 d orbitals as being degenerate. They all have the same amount of energy. As soon as you bond anything to another atom, because you're bringing electrons closer together, bringing two atoms closer together, the energy increases. So the average effect of bringing a transition metal from being a free transition metal into a complex is to overall raise the energy of the orbitals. However, the orbitals are not increased equally. That's just the average. And they actually split into two groups and they stop being degenerate. So in an octahedral complex, what happens is that you end up with two orbitals having really high increase in energy and three orbitals having a smaller increase, and you have a gap between them. Now, the reason why we get this split is because the ligands come in an octahedral pattern. So that means they're coming in at 6 particular angles. These orbitals, the x squared minus y squared and the z squared, are the ones that actually point directly at the ligands, which means they're going to be more greatly affected by the repulsion of electrons, and so they're going to increase in energy the most. These other orbitals still going to have a slight increase relative to where they started, but because they don't point directly at the ligands, the effect is a lot less. So you don't need to worry about which orbitals are the specific ones that change. You just need to know that 2 go up a lot and 3 go up a little, and you've got a split between them. And that split is going to be really important. And this is just explaining some d orbitals point directly at the ligands. Any electrons in those orbitals will experience repulsion from the dative covalent bond electrons, and it makes those orbitals high energy. Now, different ligands will create a bigger energy difference. So some ligands are able to make those orbitals split a lot, and some will make them split a little. So here's just a pattern. So for halides, the gap is quite small. Then we have things like water, and also in this category would be any other ligand that bonds through an oxygen atom. We can see it gets a bit bigger. Then bonding through a nitrogen atom gets even bigger. And then finally, we have things like cyanide and carbonyl, which is a carbon monoxide molecule, which have the biggest difference. Now, if we look at a pattern for this, halides are group 7, oxygen's group 6, nitrogen's group 5, carbon is group 4. As you move from group 7 to group 6 to group 5 to group 4, the gap gets bigger. And that's the atom that you are bonding through, where the coordinated bond is coming from on the ligand to the metal. And this is a general rule. We'll look at the pattern more specifically later on, but the general rule is halides are the smallest, then bonding through oxygen, then bonding through nitrogen, then bonding through carbon. And in all cases, we just describe this difference as delta. So just a triangle, and delta just means energy difference. Now, where this comes into effect and where it creates issues is putting electrons into complex d orbitals, so the d orbitals of a complex. Now we know the Aufbau principle says that we should always put electrons in the lowest energy orbitals first. And so when we put electrons in, the first 3 electrons go in as expected. They go into the bottom 3 electrons, but the 4th electron faces a dilemma of sorts because it could pair up in an already filled orbital. And that would make sense by the Aufbau principle in that we'd fill in order of increasing energy. And then we would fill all of the bottom orbitals before moving up to the top ones, bottom ones before top ones. Or you could have these ones that are partially filled at the bottom and start partially filling the ones at the top before pairing them up. And that would make more sense in relation to the Pauli exclusion principle, the fact that, and Hund's rule, that electrons prefer to go into orbitals singly before they double up. So what I'd like you to think about is which one of those do you think is going to be the case? Are they going to fill in all the ones at the bottom and then the ones at the top? Or do you think they will half fill the orbitals at the bottom, then half fill the ones at the top, and then start pairing at the bottom? Well, I hope you've managed to form an opinion, but the truth is, it actually depends on the type of ligand, the type of metal, and the energy difference. So here we have a case where we have a small delta. Where the delta is small, the energy difference is small, the electron is going to move up. And that's because electrons always do what requires less energy. And pairing up, putting 2 electrons side by side, you've got to overcome a repulsion force. But you also have to overcome the energy difference in order to go in here. When this difference is small, it's going to be small enough that going into here is going to require less energy than pairing up in the same orbital. However, whenever we have a large difference, the energy required to put an electron up here is greater than the energy required to pair up. And so what happens is that we get a pairing of electrons. So depending on whether the difference is big or small, large or small, you either get electrons going into the top before pairing, or you get them pairing. General rule is that halides and water, they won't pair up and they'll go into the top orbital. Ammonia cyanide, they will go in that. But that's a general rule. That's not always the case. You will be given enough information in order to make the judgment call in an exam. Now, transition metal complexes are coloured. We've discussed that. And the reasons for that are to do with the fact that we are interacting with the d orbitals, or more specifically, electrons in the d orbitals. Now, things look coloured because they absorb or they emit light. Transition metal complexes look coloured because they absorb light. And so the colour of light that they absorb is the opposite of the colour that we see it as. So that's something that you're going to have to get used to. Now, whenever a transition metal complex absorbs light, that light, we know E equals HF, or C over lambda. That light gives the energy, and that energy allows an electron to move from the lower down d orbitals to the higher up d orbitals. Whatever colour is absorbed, the other colours are transmitted. So the other colours will pass through the material. And the colours that pass through the material are the ones that make it to our eyes. And so when it comes to finding out what colour a transition metal complex is, you will need to use the data booklet on page 20, but you're going to need to use it differently to how you were using it previously. So remember, whatever color is absorbed, the opposite color is seen. So for example, if blue is the color that's absorbed, opposite on the wheel is orange, and so that's what color the compound will look. If red is absorbed, then the compound looks green. So here is it explained in a bit more detail. So you can see this is white light, and white light contains all the different colors of the rainbow. Whenever the light passes through the transition metal complex, some of the wavelengths will provide enough energy to overcome the energy difference between the lower down and the higher up orbitals. When those wavelengths are absorbed, the electron moves up. All the other colors that are not involved in this process just pass through the material. And these are the colors that make it to our eyes. Now, where we see absorption is in the 500 range, and that is the green-yellow range. So 500 to 600, that's where green and yellow are. And what we have is transmission around 400, which is purple, and around the 700, which is red. And so what we see in our eyes is a mixture of this color and this color. So the visible light promotes an electron. In this case, it's green and yellow light. For a D to D transition, it's called, because it's moving from a low down d orbital to a high up d orbital. The wavelength was green-yellow, and so the opposite colors are what we see. So red and violet mixed together makes it look a pinky purple color to our eyes. Now this is true for things in nature as well. So two of the most important molecules on the planet, chlorophyll, which is important for photosynthesis and therefore for the production of food and oxygen for us, and hemoglobin, which is important for our blood to be able to transport oxygen that we breathe in around to all our cells. They involve transition metal complexes as well. So biology is not completely free of inorganic chemistry. It's very important to it. Now this is what a molecule of chlorophyll looks like, and at the center we have a magnesium atom. So magnesium is not a transition metal, but it is a metal complex. This is the absorption spectrum of chlorophyll. So you can see that chlorophyll absorbs a lot of purple and blue light, and it absorbs a lot of red and orange light. Where it doesn't absorb, that's the color of light that passes through the molecule. So the colors of light that are green and yellow, those are the ones. So chlorophyll is a magnesium complex. It absorbs blue and red, and so as a consequence it looks greeny yellow. That's why the majority of plants look green. Now this is hemoglobin. So hemoglobin, actually you can see, looks very, very, very similar to chlorophyll. Main difference is that it's got an iron rather than a magnesium in the center. Now you can see this is the absorption spectrum of hemoglobin. Whenever, so you can see it's got quite a high absorbance of purple, but it's also got a good absorbance of green and yellow, and it's got a really low absorbance of red. And that's why it looks red. Now what happens whenever our blood binds to oxygen? This is what it looks like. Whenever it no longer binds to oxygen, it's able to absorb more red light, and then we actually start to see this color as well. So whenever oxygen is not bound to hemoglobin, we see our blood looks a bit more blue, and that's because it's got a low absorption of blue. So that's just how transition metal complexes relate to biology. Now, tying all of this together, we have something called the spectrochemical series. And the spectrochemical series helps us relate the ligand to the difference in energy and therefore the wavelength of light. So ligands are listed in the spectrochemical series, and we describe ligands as being strong or weak. If you're low down on the series, if you're a halogen, you're described as weak and you create a small energy difference. If you're high up on the series, like cyanide and carbonyl, which is carbon monoxide, you're a strong ligand and you have a large energy difference. A small delta requires less energy, which means a longer wavelength. So that means if you have these types of ligands, you're likely to absorb red and orange light, which will make you look more blue. Large ones will require more energy, which means a shorter wavelength. A shorter wavelength means that you will absorb purple and blue light, and so you will look more yellow or orange as a consequence. So if you can relate small or weak ligands to a small delta and strong ligands, ones that have carbon in them, to a large delta. So same metal with different ligands will look at different colors. And we also know that if we change the oxidation state of the metal, that's going to change how many electrons there are, and that will change the color as well. So transition metal complexes change depending on the ligands they have and on the oxidation state of the metal. Now we're going to look at catalysts. And don't worry, we're not going to look at catalysts in a great amount of detail. It's only a little bit more information compared to what you needed to know for National 5 actually, and higher. So a catalyst, as you know, is a chemical which speeds up the rate of reaction, but it's left unchanged at the end of the reaction. And there are two types. We have heterogeneous, hetero meaning different. It's where the catalyst and the reactants are in different physical states. And usually when we talk about heterogeneous catalysts, the catalyst is a solid and the reaction mixture is either a gas or a solution. And then we have homogeneous catalysts, homo meaning same. And that's when catalysts and reactants are in the same physical state. And usually we're talking solutions. And we're going to look at how the different types of catalysts work. So a heterogeneous catalyst, usually whenever the catalyst is a solid and the reactants or gases are dissolved. Now what we have is a catalyst which has a surface. And our reactants, in this case, ethane or ethylene as it's called in America, and hydrogen, what's happening is that they adsorb. Now it's not absorb, it's add with a desorb. And what adsorb means is that you only bind to the surface. Absorb means that you get drawn within the catalyst. So that means the way a sponge absorbs water, the water goes the whole way throughout the sponge. If a sponge adsorbed water, the middle of the sponge would be dry, but the surface would be covered in water. So that's the difference between adsorb and absorb. And catalysts adsorb chemicals. They go on the surface. What that does is that the transition metal is able to bond to the different atoms and break them apart or make the bonds weaker. And this is happening. So the hydrogen is being broken apart, but the ethane is adsorbing to the surface and that bond's getting weaker. And it's also bringing everything into the correct orientation such that it can react. So reactions adsorb, and the part of a catalyst where this happens. So it might seem that a catalyst surface, we might think of that as being all the same, but actually it's not. You'll have corners, you'll have edges, you'll have ledges. on the surface of a catalyst, and depending on whether you're a corner, whether you're flat, whether you're an edge, etc., molecules will be able to bind in different ways. The areas where molecules can bind in the best way for a catalytic reaction to happen is called an active site. And if you do biology, you know that an active site is the part of an enzyme that also does catalysis. Sorry, I'm not able to speak very well on this slide. Now, how this happens is because the transition metals have d orbitals that are empty or have unpaired d electrons. And what you actually are forming on the surface is a sort of transition metal complex. And that's why we call it an activated complex, because it's a transition metal complex, but the reactants are being activated, they're being made more active, more reactive. And by doing so, it makes the total energy necessary for this process lower compared to uncatalyzed reactions. And then obviously at the end of the reaction, your product is released from the surface and the surface can be reused over and over and over again. Homogeneous catalysis or homogeneous catalysts are less well understood. However, we sometimes do get evidence for them happening. So what happens is that it's usually in solution and reactant molecules replace some ligands on transition metal complexes. So maybe you have a water molecule as a ligand on a transition metal complex. When you introduce it to a chemical reaction, maybe that water gets substituted for one of the reactants. The transition metal is able to change oxidation state. We know that that's a really common thing. And by doing so, it might be causing oxidation or reduction of the reactant molecule, which will make the reactant molecule more reactive. And again, it's forming an activated complex. And again, creates a lower energy pathway. Now, we can see evidence for this happening, either the reactant molecule becoming part of the complex or the change in oxidation state, because often if we do homogeneous catalysis, we see reversible color changes. For example, when cobalt catalyzes the decomposition of hydrogen peroxide. So that's a very, very common reaction. Decomposing hydrogen peroxide, you make hydrogen and oxygen. But it can be catalyzed by cobalt. Now, cobalt usually dissolved in solution has 6 waters around it, so it's a hexa-aqua complex, and that is pink, very bright pink. When this reaction happens, and it starts to catalyze this reaction, you see the solution turn green. And that's because the cobalt is being oxidized to cobalt 3+, which makes it look green. And then when the reaction is over, you can see the solution go back to being pink. And that's really strong evidence of what's happening. Now, all I'll say is catalysis and how catalysts work is still an ongoing area of chemistry where we still don't know a lot. But it's an area of chemistry that needs to be really well understood. Catalysts are going to be key to a lot of the development of green energy sources. Solar panels rely on catalysts. Being able to get electricity out of renewable sources relies on catalysts. And so it is a really interesting area to think about working in that actually makes probably billions of pounds every year for the chemical industry. And an awareness of inorganic chemistry leads to that. So inorganic chemistry is often seen as one of the more boring versions of chemistry, but actually it's one of the most important ones to help us move forward technologically. And catalyst is one of the ways that that can be done. So that's my sales pitch for inorganic chemistry, and that's also us finished with catalysts and transition metals, and in fact the inorganic chemistry part of Unit 1. So I thank you for watching this, and I will see you next time.